Hello, everybody, and welcome to the Cosmos Show, the place to be if you're curious about the universe. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here you can pick the brain of astrophysicists, get advice from a space doctor, learn what Nobel laureates have to say about life, and learn about all the cool stuff happening up above your heads, all in the same place. You can chat your questions on Twitch and YouTube, or you can call in and ask your questions by dialing 929-205-6099. And the meeting ID you'll need to connect with us is down at the bottom of your screen. So give us a call. We'd love to hear from you. You can join us every other Tuesday live on YouTube and Twitch. Today's program is all about preserving dark night skies. And we're going to hear from one of today's great dark sky conservationists, John Barentine. But before John joins us, let's introduce our co-stars. So first, postdoctoral scholar from the Simons Observatory, it's Nick Galitsky. Hey, Nick.
Hey, Sam.
Thanks for joining us. Next, PhD candidate in astrophysics from the University of Chicago and the host of her own YouTube show, Nora's Guide to the Galaxy. It's Nora Bailey.
Hello, happy to be back.
Thanks for being here, Nora. Next, medical doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Nice to be here. Hi.
Thanks for being here, Danny. And last, but certainly not least, Deputy Director of Education and Public Outreach from the Vera Rubin Observatory. It's Dr. Lauren Corlies.
Hello.
Hey, Lauren. All right, so today it's Nick's turn to tell us a little bit about what he's up to. And so, Nick, we're all yours.
All right, yeah. So we're going from the big picture to the very little in the world of the experimental astrophysicist. So if you go to the first slide there. There we go. So starting out, this is getting into what I study, which is the cosmic microwave background, which is at the very end of this, classic diagram showing the history of the universe as we know it, where, time of now, the present day is at the right side of it. And then you look back and you see all these galaxies and you look farther and farther back, and galaxies fade out as before they've formed, and eventually you get all the way to the Big Bang, but we can't actually quite see the Big Bang. The universe was too hot and dense right after that event, and so we have to wait a few 100,000 years for the universe to cool down, at which point we get a radiation from what's called the cosmic microwave background, which is shown there almost at the very left of the picture. Yeah, so and that's often described as like the glowing ember of the Big Bang, or kind of the remnants of the Big Bang. So this is where we can see as far back in time as possible, almost 14 billion years ago, the very early universe, about 375,000 years after it formed. So that's what I like to study. That's what I'm working on. Of course, it's a little bit of work to get there. So let's go to the next slide and see if the video will play. Ooh, I got it working, maybe. All right, this is just a fun visualization I love to show. I wish I could say I came up with it. I did not. I stole it off the internet. I think Dylan Berger is the person who put it together. But what's so wonderful about this is it shows the cosmic microwave background in all its glory. And since this is the farthest away we can see, you can actually think of the Earth inside of this sphere. And this sphere represents the entire observable universe. That's everything we've ever seen and it can see, just due to just to the fact of how the universe we live in and the fact that light travels at a finite speed. And the other thing you'll notice is it's this weird splotchy kind of Rorschach test going on. You see what you see. But what that is little temperature fluctuations in the early universe. And it's kind of crazy how small these temperature fluctuations are. They're, 1 part in 10,000 is what I'm showing you here. And the ones I'm looking for that can tell us even more information are even smaller, just 1 part in a million or so. So really faint signals. But what's cool about it is because it's this kind of remnant glow from the Big Bang, is it can tell us basically about the structure of our universe. It's, it really gives us information about how the universe formed and how it evolved. So that's kind of the big picture of why I'm excited about it and what's cool about it. Then let's get into the nitty gritty of how we actually do that. So go to the next one. We'll go there in a second. And this is, a long process. It's taken us about 5 years to design and build these. But you go out, you design and build a telescope. In our case, for the assignment's Observatory, it's an array of telescopes. We have these 3 small aperture telescopes that we're building. On the right there, you see the full array and its CAD rendered glory. That's about, each one of those circles is about 20 meters across, or about 60 feet across in each one of these telescopes. The size of a small house. And then that middle picture is the actual camera. And that's the camera I've designed and built over the last few years. And spend a painstakingly long amount of time with in our lab. And it's about 6 feet tall or so, and about 6 feet wide. So it's me-sized, a bit taller once it's on the cart. And the left image there is what happens if you cut it in half. And it's kind of, I would describe it as like a Canon DSLR camera, because the cylindrical section out front is just all the lenses. And we actually do have a refractive telescope. So we have 3 lenses. In our case, they're made out of silicon. And then at the back end of it is where the detectors are. They record the light and convert it into an electronic signal that some additional electronics then writes into a disk. And that's kind of the basic premise of how this works. And so then if you go to the next slide, the CAD looks very clean. This is what it actually looks like in the lab right now downstairs. And you can see it pretty much looks like the render, but we've got all sorts of wires coming off of there, reading out the temperature of things, and reading out the detector signals and running the cryogenic systems. And this is where I talk a little bit about the complicated part of looking at microwave light is at a very faint signal, is you really want your camera to be as sensitive as possible. And one of the main ways we do that is by cooling it down, which is something I'm quite good at. It's a subfield of physics called cryogenics, which is the art of getting things cold and keeping them there, because they really don't like to be that cold when everything else around them is really warm. So you go to the next slide. And this actually shows the last 60 days of that cryosat. So this is what we've been up to for the last 2 to 3 months. And you can see we started the cool down. I think that's started out in June, mid-June, we started the cool down. Room temperature, and then you turn on all the bells and whistles there, the cryogenic equipment, and it slowly cools down. After about 10 days, we get things down to about 40 Kelvin and 4 Kelvin. So you're seeing the different stages separate out. The 40 Kelvin is an insulating stage. The 4 Kelvin is an insulating stage. Then we turn on another piece of equipment, our dilution refrigerator, and that pops it down pretty quickly to 1 Kelvin, which is what our optics are at. So all our lenses sit at 1 Kelvin, and then our detectors are a special type of superconducting detector, and they like to operate around 0.1 Kelvin, and our actual base stage there you can see gets down to about 0.03 Kelvin, or about 30 millikelvins. That's what we like to sit at as long as we can, hanging out there. And you see all the the temperatures drop out, or they jump up and down. They're doing all that stuff. That's us running tests and trying to understand what's going on in there. And so getting into the what's going on, this is getting into what I've really been up to. You go to the next slide. And this shows the inside of the camera. So I told you the lenses are in front of the piece on the left-hand side. This is kind of looking at it if you opened up the back side of the DSLR camera and you're looking at the guts of the thing. This is our actual camera array. And what we got in there this last couple months is really exciting. After 5 years of waiting, we finally got the first detector array. And so that's that hexagonal piece down right. That is the actual detectors we use to look at the cosmic microwave background. Our first one that we got to install, and we're trying to understand how well it works and what quirks are. And actually the top right is even cooler because, telescopes are just collecting light. We collect it with lenses, but those are called feed horns, which actually couple the light coming into the detector elements. And if you look right at the center of those little circles, they're little cones. And right at the bottom of the cone, you see this little X pattern. And that's actually the detector element itself. This is kind of fun because we work in millimeter wavelengths. The detectors are actually physical scale where you can visually see them with your eyes. So that's really exciting to be able to see that. That's the one collecting the light. And we're just trying to figure out if it's working properly. And this gets into the kind of funnier part. So next slide. I wanted to show picture me for scale. That's how big it is. Hanging out with our camera. And then the next one is where things get funny and where you really know we're an experimentalist. So go to the next slide. Should show the cooler. There we are. All right, so this is our readout electronics. And so we have this really fancy, incredibly complicated custom detector arrays coming out into our electronics. And we are worried that this one piece of our electronics was causing additional noise. It was basically making our signal noisy when we come out because we thought it was coupling to the room temperature. You know, the room temperature changes. Our lab is effectively outside here in San Diego, so the room temperature fluctuates a lot. And so, you know, how do you isolate it from the environment? Well, you put it in a cooler with a heater and a little cooling unit, and you can then servo what temperature it serves at. Then we had an additional problem, and this has really been my life the last couple of weeks, is the guys next door to us in the lab, they kept opening the doors at 6 a.m. I'm out here in San Diego, and we get this really nice mist coming in off the ocean at 6 in the morning. And it turns out one of our electronics systems on the right there in that computer rack, you can see all the wires flowing out of. It turns out that one's gulping down air with a bunch of fans. And it turns out when you open the door at 6 a.m. and it's misty out, those fans gulp down a bunch of moisture and get your electronics wet. And they really don't like that. Really don't. So how do you solve that? Maybe you get a nice fancy solution. We do have one of those incoming for when we actually go to site. Of course, foggy air is not an issue at 17,000 feet in the Atacama Desert. So not really something we planned for. So you find a quick solution and you go to the next slide and you build the DAG House. And so this is what me and the graduate students did is we roll down to the local Home Depot and you buy a portable greenhouse and you hook it up to a dehumidifier. And then that makes your electronics too hot because now they're in a little enclosed room. And so you throw a portable AC unit in there with it and you patch it all together and you hope it still works. And I can successfully report that it has. We've been running for a week. No problems, no issues with moisture anymore. Able to collect more detector data and trying to understand what our noise properties are and realize it's no longer being caused by moist electronics, which is fantastic news for me. And so that's kind of what life looks like as an experimentalist, at least for the last couple of months of in our lab. Anyway, those are all the pictures I have if anyone has any questions.
I just love that Home Depot is a part in solving the unsolved mysteries of the universe.
Absolutely. Boy, anything that'll give you a next day delivery when you got something like this happening.
It's amazing to me just how different our worlds are as a theoretical astrophysicist. I would be totally hopeless at any of this. This is amazing. I can't believe how cold you get that detector. I did not realize. That's insane. So you said that the whole observatory thing is about the size of a house. And this is, you know, your camera that you're building. I was just curious. I don't know much about this observatory. When is it open? Like, is this a new piece of equipment or is this a new observatory? I guess that's my question.
It's a new observatory and new piece of equipment. And I think that's the kind of weird thing about the CMB is probably also for observationalists here, you know, a lot of time you apply for time on an observatory. We don't really do that because we're looking at the CMB and it's like, well, what do you want to observe with the CMB telescope? And it's like, well, the CMB. And so what we basically do is we'll get these telescopes set up and we'll stare at the same 10% of the sky for 5 years straight and just staring at it. We'd stare at it more, but it sets sometimes. So we got to go look at a second patch of sky. And so we alternate between two patches of sky, and then we just stare at them for 5 years with 3 telescopes to get the sensitivity we need, because it's just a really small signal. And that's all we do. And it's an observatory because these are called the small aperture telescopes. They're a 0.5 meter aperture, which is small in the microwave at least, coupled with the large aperture telescope. Classically, we're really great with our acronyms here, the LAT and the SAT. And the large aperture telescope is a 6 meter dish and it looks at about 50% of the sky. It is also just a survey thing. You don't really do targeted stuff with it. It's just, but it also does some galactic science, but it's It'll do cluster science, and it really comes down to small, angular scale. And this is getting into the CMB. There's the science we're going after, which is very much how did the universe begin is really the kind of question we're trying to answer, getting into inflation, if you're familiar. And that one, you don't need very good resolution. So you can go with a 0.5 meter aperture and get really blurry images of a huge chunk of the sky. And that'll get you the science you need. And then there's a different set of science you can get where you can constrain like neutrino mass and do cluster science and galactic science technically, and some other things with it with a better resolution of a 6 meter dish. And so both of these are new. They're going down to a site in the Atacama Desert, and they're going to observe the CMB for 5 years to hit the next bump in sensitivity and resolution we can do there. And it's a little weird because there are existing telescopes at that site that we like kind of two of those groups of telescopes have come together in one collaboration. Then there's another collaboration, the class telescopes hanging out and having a good time that are also observing the CMB. And it's this little cluster of CMB folk hanging out in this little plateau that's a couple football field size at 17,000 feet in the Atacama Desert. And we're a few miles away from our much better known neighbors, ALMA, the Atacama Large Millimeter Array, which is, we're puttering along with our little CMB project off here, and all this massive $1 billion array of telescopes that you do apply for observing time on, wherever else is doing its thing down the road. And we really like them. They're actually really great neighbors because they help us clear the roads and help us transfer data and stuff.
So when is first light expected for these?
God, that's a sensitive question for an
Sorry.
we have a running joke because that's we always have that in our presentations and stuff. Obviously the last couple of years have not been great for schedules. We're tentatively saying 2022. I'd like to see this telescope down in Chile in about a year is what would make me really happy if that worked out like that. Assuming we don't have any moisture related incidences between now and
then. So Nick, I have a couple of questions that I think folks watching this are going to be interested in. So the first is kind of like the big question is, so why does it matter to get more detail in the CMB? What are you actually looking for? What do you hope to learn from this? And then a specific question about the 3 telescopes. You mentioned that the 3 telescopes are better for sensitivity, but why not just one big telescope? Why 3 small ones instead?
No, that's a great question, and that was part of our design thing. So the first question is what are we specifically going after? And it's this polarization signal, and this is get a little nuanced into the CMB side of it, but that's fun. We can dig in a little bit here. And so I should say the kind of the intensity measurement, the absolute signal from the CMB has been pretty well measured by a number of satellites, most recently Planck satellite, as well as some other observatories. But the polarization signal can actually tell us quite a bit more information. So this is the polarized light, and the light from the CMB is polarized. And the satellite that flew, Planck, had some sensitivity to polarization, but not very. So you can effectively say they took a fairly noisy picture and it didn't get us to the sensitivity level to uncover this special polarization signal that we hope is there, that we think is there. That would be an indication of this first fraction of a second after the Big Bang. And the idea is this, in the first fraction of a second, the universe expanded incredibly rapidly, and it generated a bunch of gravitational waves that then rippled out through space. And by the time you get to the CMB surface where it's starting to release photons, we can observe that would effectively, these kind of gravitational waves rippling out through the early universe would distort the polarization signal in just a certain way that we'd be able to look at it and be able to tell, what happened immediately after the Big Bang. So that's like why it's such a big deal, is if we were able to find it, it probes the earliest part of our universe that, very few, if any, other experiments can probe. So that's the exciting thing. Why it's hard is because depending on, effectively how much energy was involved, directly couples to how big the signal is. And we've already started lowering the upper limit on it and no detection. And so now it's like, okay, we need to build better telescopes that can bring it down a little bit more. To your question of why 3 of them, there's two reasons. Actually, one is we have issues with foregrounds. It's not just the CMB that emits microwaves, our galaxy does too, from both synchrotron radiation and thermal emission from dust. And so we actually have multiple frequency bands. And this is probably something people who build telescopes can understand is if you have a refractive system and you want multiple frequency bands, it's really hard to get all your optical throughput to work with without having issues with chromatic aberrations effectively. One optics does not fit all wavelengths. So we have different sets of optics with different AR coatings and technologies, and including detector technologies actually to cover a wider frequency range to understand that. It's also a sensitivity game. Like I said, it's a really small signal and we're impatient. So if I built one telescope and it took me 10 years, I could build two telescopes and it'll take me 5 years. And so, well, they're kind of expensive, but that seems worth it because I'm in a hurry to learn about the universe. So that's the other reason. I'd love to put all the detectors in one big telescope. And actually the Large Aperture Telescope did that. They have a similar camera, except it's also cools down to 100 millikelvin. And it's about 2.5 meters wide. I can walk inside that telescope camera. It's wild. They did it. They pulled it off. It's very challenging to do. It's risky for a number of other reasons. And it just doesn't quite work out in terms of the complexity and how to actually mount it and point it at the sky versus splitting it into multiple small ones. And this kind of also couples, it was like a natural separation by frequency regime. Anyway, we can only build our optics as big as about 50 centimeters. So we can, that kind of made a natural selection. And then combining them into a single one added some more complications in terms of the scheduling and, and so on and so forth. So I would say it's to reduce cost and make it more flexible, reduce risk as well for our particular program. Great questions, though. Yeah.
Very cool. Thanks for that. Lauren, I think you were about to ask something as well.
Yeah, I was just going to follow up and say if you could say something about the team of people that you're working with to build the telescope. I'm assuming that's to be some of the fun part is like getting to bounce ideas off each other.
Yeah. This the DAG House, the dry air conditioned greenhouse, came together with me and some graduate students hanging out for about 5 hours or not 5 hours, for a couple hours, searching things on Home Depot and be like, oh, this one's in stock at that store and I can go pick it up tomorrow. So we got a fantastic team. I mean, the whole collaboration is big. It's big for me. I don't know, some of you, I don't know how big Vera Rubin is these days, but we got about 300 people. Big for me. Something like Vera Rubin, once you include the team of engineers, it's probably way above that. So we got about 300 people, but a lot of those people are doing, the kind of the theory, the analysis. It's like, what could we achieve with this? The forecasting, they're taking simulated data and seeing what are we actually going to achieve. And then, like I said, there's 3 of these telescopes and a large aperture telescope. And so then you divide that up, and even the experimental team's probably about 80 people, but divided up among a number of institutions. So the SAT team here at UCSD is I'm going to get the number wrong, but it's about 8 people. It's me, the professor, PI Brian Keating, and Cam Arnold is another professor working here, and then graduate students, of which I think there's about 6 with varying levels of commitments. So say Tran and Michael and Joe and Max. Those are the crew that I'm going to leave a couple people out. Apologies, but that we were sitting down and trying to figure this out, and realizing this moisture issue and how to go at it. And actually, really exciting. We just got some undergraduate researchers in the lab this last few weeks as well. So we have undergraduates that we task with little projects to include some of the data analysis coming out of this. There's a lot to understand about how our detectors are behaving and the various noise properties. And we see magnetic field pickup. And so let's explore the magnetic field pickup. Where is it coming from? And what sources are, and how can we mitigate it? And so little things like that we're throwing at undergraduate researchers coupled with graduate students. Just in the terms of the normal lab hierarchy. And I'm excited about the undergraduates because these are the first undergraduates we've been able to work with in over 1.5 years, which is big for us because there's a lot of little things around the lab that are really good to learn on that we love to be able to delegate to new people in the lab. So I don't know, that's kind of a quick run of the team. They're fantastic people to work with. And then obviously we present our results on calls and get feedback from other people at other institutions. And then there's a team at Berkeley and Princeton that are working on the other two receivers right now. And so we talk with them and swap notes about who's, doing what and who broke what and how we can avoid doing that and things like that. Yeah.
I've got a question for you, Nick. How and at what point did you decide to go into this field to begin with? I'd love to hear this. I bet there's a good story.
No, that's great. Yeah, because I think it kind of accidentally, I would say accidentally, but it wasn't an accident because I'm very hands-on. I'm the guy who played with Legos and Rector sets and always building stuff. So I like having things hands-on. I don't think I realized that instrumentation was a thing. And I think a lot of people don't really realize that instrumentation is a thing, or the experimental side of astrophysics. Somebody has to design and build the telescopes. And a lot of people don't realize that, or that's like a research part you can be, involved in. I didn't when I first started as an undergraduate. And I think the first few projects I tried to get involved in, and maybe was involved in to a limited extent, were more on the observational side. I think that's probably where I started out thinking where I was going to head was let's go look through a telescope, get some data and process and analyze the data. And I still do that. Experimentalists, we try to be jack of all trades and, build it, understand how it works, get the data and then understand what the data tells you. So we fit a wide range there, but pretty much immediately in my undergraduate, the first two research projects I ran was some level of instrumentation. And that was probably because those, whether I acknowledged it then or not, were the most exciting things to me when I saw, the kind of research I could do. So my first one was at Jet Propulsion Laboratory. I was doing a little project, summer project, trying to build a seismometer to put on the moon to detect dark matter. I still remember it because it was a cool idea. It was based on the fact that we were obviously going back to the moon any day and would have opportunity for all these little piggyback experiments. So obviously that didn't pan out, but fingers crossed one of these days. And then I built another one where it was actually very full circle. It was a researcher doing atmospheric water vapor detection. Hey, there you go. For site exploration in Chile. And so they were building that to do a little radiometer. I think the guy I was working with there, Simon Radford, he recognized that maybe I was kind of good at that. He was like, maybe you should talk about doing that. And he guided me into applying to the grad school. I eventually went to the University of Pennsylvania, where I did I designed a camera. Hey, there you go. Now I'm doing the similar thing, but that was for a balloon-borne experiment. And if you really want some wild experimental research, do a balloon-borne project with NASA, because it's basically building a satellite in a shoestring budget in your garage and hoping it'll work when you throw it on a balloon out of Antarctica. Sometimes it does, sometimes it doesn't. This is what I've learned there. And that's also why I'm now doing a ground-based telescope, because I'm pretty sure this one won't crash into the ice sheet.
So you're headed back to Antarctica at some point then?
I hope so. Yeah. Our current, so this one's going to Chile, but the other, my other one that I've been working on off on, we're kind of in between funding cycles, is one that we're actually trying to fly out of New Zealand this time. Antarctica's cool, but it's kind of a pain. Logistics are a nightmare. So we're thinking of shifting which aspect of the NASA proposals we're applying to, but yeah. Been down to Antarctica twice to fly balloon-borne telescopes as a as a part of being an experimentalist. Yeah, get to go to some cool places. Technically, this telescope was built in Italy, so I got to go to Italy a couple times to check that out. That was rough.
Well, if you need a doctor, just let me know.
Will do. I hope not, though.
It's funny. I actually did not know that instrumentation was like a subfield of science until I was literally at like grad school open houses, and like the faculty were like, "I do instrumentation," and I was like, "Isn't that just engineering?" And I very much offended some people. It's not. I learned.
Well, thanks so much, Nick. That was fascinating stuff, and thanks for sharing those personal stories as well. That makes it all the more interesting. So
yeah, and hoping the next update I did, hopefully we'll have our next step is taking the lens cap off and doing some optical tests. So fingers crossed that goes smoothly. It almost certainly won't, and I'll have more stories.
Well, if Home Depot plays another part, please tell us about it.
Go, will do.
All right, we're gonna move along now to Nobel Notes. If we can go back up to that lovely picture of Einstein at the very beginning of the slideshow. So tonight's theme is preserving dark night skies, and it's a long haul process. It's going to take a lot of people all working together to ensure that we can preserve dark night skies for generations to come. Not unlike the long haul process that Nick is working on his research and what's going on the Vera Rubin Observatory and all the big collaborations to build new incredible instruments that'll help us understand what we don't understand about the universe. So the Nobel Note comes from Albert Einstein tonight, who won the Nobel Prize for work on the photoelectric effect and Brownian motion. Contrary to public belief, he did not win it for general or special relativity. But anyways, his quote tonight reminds us to keep working on the problem at hand. So he says, it's not that I'm so smart, I just stay with problems longer. And I'm not totally sure if that's true. I think he might have actually been smart as well. But I like this idea of diligence and keeping with the problem potentially longer than other people might. So if any of the co-stars can relate to that, if we have any ideas or comments you'd like to add, please do so.
Yeah, I definitely am not quite convinced that Albert Einstein was not just actually smart. I could think about like gravity for a really long time and not come up with general relativity. But I think to me this, so I can't remember if I've spoken about this on the show before, but I was a non-traditional student, so I didn't return to grad school until 8 or 9 years after my undergrad. And one of the reasons I hadn't gone straight into academia, well, when I was in the Navy, but two, was because you hear so much about Einstein and these big scientists that have these big paradigm shifting views. And I always thought, well, I can't do that. That's not going to be me. I'm not going to be the next Einstein. And I think this is really important concept that there's so many scientists out there that are doing excellent science, and it's really important. And that's how we advance the field. It's not all Einsteins. Einsteins are the rare exception. And so for me, that was really inspiring to be able to be like, no, even if I'm not going to come up with something that's going to completely revolutionize everything we know about the universe, I can still contribute to the scientific knowledge just by working on a problem that interests me. So.
And I think really what he's getting at here, at least the way that this quote sits with me, is that he's kind of emphasizing the fact that it's really more about grit. Finding a problem that seems really meaningful and there's like a real purpose to trying to solve it, and just sticking with it, through challenge after challenge and just making it happen. So I think everybody can probably relate to that in some way.
Yeah, you don't have to be a genius to have grit. If anything, Wyoming stargazing has been about blood, sweat, and tears. It hasn't been about intelligence.
Same with orbital biodesign.
I think for me, the thing that stuck with me is that sometimes things just don't click immediately. And that doesn't mean that you'll never understand them. It's just literally sometimes things just take time in your brain. It's just like working in the background, and you'll be doing something 3 months later and be like, oh, I understand now. And you'll have an idea. And so sometimes you just do need to give yourself that space and that time just to like sit with something before it really clicks and you get to make that fun connection. So whether that's in classes or in research, or if it doesn't make sense immediately, that doesn't mean it will never make sense. It just means you got to give yourself some time.
I like to use the word percolate for that.
Yeah.
It just seems
that's
so
actually perfect. The word I was thinking of. Yeah, that's why I'm like going like this. It's like bubbling up. Yeah.
Yeah, so true.
Growth versus what's the mindset, right? So instead of like saying, oh, I'm not smart, so I can't do it, like it's not about your intrinsic property of whether or not you're smart or not, because that's something you can't control, but it's about your actions. It's about tackling the problem and trying to grow into being able to do it regardless of whether you're smart or not.
Yeah, having an internal locus of control, I've heard it called before, versus an external locus.
Well, thanks everybody for your comments on that. Appreciate it. So we're going to roll into virtual stargazing now. We connected a little while ago with our virtual stargazer down in South Africa, Ben Coley from Celestial Events. So we're going to play some clips of some of the images that he took for us. And then we're going to come back after that with our special guest, John Barentine. So enjoy the virtual stargazing clips, and we'll be right back with our special guest. We'll see you then. Hello, everybody. Samuel Singer here, the founder and executive director of Wyoming Stargazing. I'm here with Ben Coley from Celestial Events, South Africa. He's been good enough to join us in the middle of the night in South Africa, middle of the afternoon here in Wyoming, to do some virtual stargazing with us. So Ben, welcome, and thanks so much for being here.
Thanks for having me back again, Samuel. Looking forward to showing you some more Southern Hemisphere delights. So to sort of move straight into it, well, the first one I've got lined up for you is actually one of the most famous deep sky objects that we have down here. Even though it's very, very small to the naked eye, it looks like a very faint star right on the edge of naked eye visibility. Through binoculars, you can see 5 or 6 stars, but hopefully through the telescope, I'll be able to show you a photo of somewhere between 80 and 100 stars in an open cluster that we lovingly call the jewel box. And the jewel box is situated right next to the star called Mimosa in the Southern Cross, or Crux, the smallest of the 88 constellations. So hopefully, let me see if I can open the image for you, and I'll share my screen. Okay, so yeah, this is one of the most beautiful open clusters in the sky, and it's sometimes difficult for open clusters to be done justice with photographs, but I think this one really does do the job. So I'm just going to share the screen for you now.
So much suspense.
Okay, here we go. Hopefully you guys can see
yeah.
that. Now that's just the very quick raw image. So that's the 60-second exposure taken with my 10-inch Meade LX200 mounted on the Celestron equatorial mount. So let's just see if we can coax a little bit more detail out of this one. Okay, so I'm just going to do a very quick curve stretch and see if we can bring out some of the fainter stars in there without hopefully blowing out the center too much. The ones I really want to show you that you can see beautifully well is that line of 3 stars right here in the middle. Let me just zoom in a touch for you, because we lovingly call these the traffic lights, and that's kind of where the object gets its name from, because there's lots, even though you can't necessarily see it here, even when viewed through a telescope, you can clearly see that there's lots of different colored stars in here. So hopefully you can see here we've got one nice red star, and then actually I have to say I think we've blown it out a little bit too much with too longer an exposure, but this star is a more of a sort of a yellowish, and this one is actually comes across as a bluey green. So we lovingly call this the traffic lights, and it was actually discovered by a Frenchman from his observatory here in South Africa at the base of Table Mountain by Nicolas de la Caille in the 1700s. And then it was John Herschel who actually then went on to describe it as a casket of variously colored precious stones, which is where the name the jewel box actually comes from.
Very cool. It reminds
it's
me of a binary star system we have here in the Northern Hemisphere called Albireo, also known as the Cub Scout star. There's one orangish red giant star and then a younger blue giant next to it. And so you can really see the color variation of the 2 stars next to each other.
Yeah, we're very lucky. We do get to see Albireo. It's probably about midnight tonight. It'll be high enough to actually get a look at, but it never gets above sort of 20 or 25 degrees here, so we can definitely see it. But it's yeah, not perfect. But this one really is a showstopper, even through the telescope, through outreach evenings that we do, purely because even through binoculars, you can just maybe sort of see maybe this star, this star, this star. You can kind of almost see this triangle, this A shape that you can see here. But then through the telescope, it just comes to life, and you can. It's one of the few open clusters where you can actually really see the differences in color.
Yeah.
Now, whether that's because of its position close to a very famous area of sky here, also next to the Southern Cross, called the Coalsack, which is a large dark nebula. So it looks like this black patch in the middle of the Milky Way. Interestingly, there's a Bushman tale of where the gods got very upset because they'd missed a zebra on a hunting trip, and in a fit of rage, he kicked the Milky Way, and this chunk came flying out of it to become the Small Magellanic Cloud, and this coal sack is the scar left behind from this sort of fit of rage.
Very cool.
But it's quite possibly because this cluster is very, very close to that coal sack, it's very difficult to gauge the exact distance to it. And that's also going to have an effect on the colors of the stars coming through. So we do get a little bit more perhaps reddish color than the star themselves actually is exhibiting, because of that, the dust blocking some of those other wavelengths of light.
Very cool.
So we think it's about 6,500 light years away, but so we're not 100% sure, which is it's still far, but the coal sack is much, much closer to us. So that light does have to pass through sort of the edge of that dark nebula. And it's also considered to be one of the youngest sort of, open clusters in the sky. I mean, again, because of the difficulties in viewing the stars clearly, there's a bit of a discrepancy, but the younger estimates have it at only 6 or 7 million years old, which is, in terms of how open clusters go, that is still pretty young. And yet we've still got one star here, which is a red supergiant. I think it's burning at sort of 80,000 times brighter than our sun. So it's already on its way out. So there were some big stars formed in this cluster.
Very cool. Yeah, it's beautiful.
Yeah, one of my favorite objects down here, and it has a lot of notoriety down here. It's actually considered one of the big five of the African skies by some.
Nice. So which of the 5 big animals would that correspond to?
Well, that's a good question. I should know that. I was actually in the Kruger today. I was lucky enough to get out, and I did see 4 of the big 5 today on my safari that I did. So we'll call this one the leopard, I think, because it's quite tough to see, but when you do get a close-up look at it, it really is it's pretty spectacular.
I love it. So we'll start calling it the leopard cluster here.
The leopard cluster, I like that. Yeah. All right. The other one I was going to show you this evening is a little bit low on the horizon now, but before we came on air, I was able to have a crack at it. Let me just read off. Now, this is a very interesting object. So I was looking for something sort of new for everybody. And it has quite a strange background. It's actually an emission nebula, which is part of the Eta Carina, or the Carina molecular cloud, with the very famous Eta Carina nebula we looked at the other week. And just on the northern tip, although it's still associated with it, is this little area of nebulosity, which is called the Gabriela Mistral Nebula, I've since discovered. And that's actually named after a Nobel Prize winning Chilean poet, because it's supposed to look rather like her face profile, the gas that's been sort of cut out by this young open cluster of stars. Okay. So I took a photo of it a little bit earlier and just did a very quick edit on it, which I just want to show you guys. Let me just share the screen, and you'll have to sort of bear with me a little bit while I try and explain this profile, but then I'll show you a proper photograph of it taken from, honestly, I forget if it was the Hubble or the European Space Agency, but then you'll be able to see it a little bit better. Okay, so this is the area of nebulosity. You can see this beautiful pink color, again, caused by that ionized hydrogen. So this is a big cloud of molecular hydrogen gas, basically. And in here is a little star cluster where young stars, a bit like the jewel box that we just looked at, but young stars being formed still within this sort of parent nebula. And because they're so energetic and they're blasting off X-rays and all this other high frequency wavelengths, they've sort of sculpted this shape in the gas. You can sort of see this ridge line here. Now, if you could imagine this little nubbin here is supposedly the nose of this character, and this is sort of her forehead. It's upside down is the way we're looking at it, but this would be her forehead, this would be her nose, and then her lips, and then round to the chin. But as I said, this was a little out of reach perhaps of my equipment, but when you see it in hydrogen alpha and O3 filters, which I'll show you now, it really is quite a spectacular image. Let me just dig it up for you. Okay, here we go.
I'm curious which astronomer recognized this Chilean poet in this object.
That is quite a good question, and maybe for reasons that are perhaps apparent.
Totally profile now.
See, now you clearly see it. So with some proper stuff, you can see the line of the forehead, perfect little nose, and even where the lips and the little chin end and indentation. Yeah, quite who decided it looked specifically like her, I don't know, but I can tell you it was James Dunlop, the Scottish astronomer who discovered it in the sort of the mid 1800s. He was also the same guy who discovered the Centaurus A galaxy and the Pavo globular clusters that we've looked at recently as well. Yeah, but I don't know who actually made the connection between the two of them. But yeah, it's a beautiful image, and you can see this sort of the different colors here. This is actually more oxygen, and then the hydrogen around the outside. But from one side to the other, you're looking at about 35 light years across. And it's far away, just like everything in that Carina cloud complex. It's such a deep complex that we're never quite sure how far we're looking, but estimates are around about 7,500 light years away. So yeah, that was a new one for me, a bit of a gem, and that was very nice to discover. And yeah, and here is the little open cluster here, which is known as NGC 3324. It doesn't have an official name, but these are the young stars which are sort of blasting away the gas from around them and sort of revealing themselves in this cloak of hydrogen. Very cool.
Very cool. And are those like dark colored kind of little blobs I'm seeing throughout? Are those like the Bok globules that I've read about?
Yeah, exactly that. So those are, as you said, Bok globules, which are named after Dr. Bok. I think it was not Dr. Spock, Dr. Bok. I think he was a German astronomer, and he was the first one to sort of figure out that these darker nebulae, or these darker patches that we can see, are actually areas of that hydrogen that are becoming very, very tightly compressed now, and it's within these that new stars, sorry, excuse me, that new stars are going to be beginning to form. So that pressure is going to get so intense that hydrogen is going to be shaped into a ball and crushed until it heats up, and eventually, hopefully, nuclear fusion will occur, and that hydrogen converts to helium, and we have the birth of another star.
Very cool. I think the pillars of creation are examples of larger Bok globules, right?
Yeah, as far as I understand it, I'm not quite sure what magnitude of Bok globule becomes something else. But yeah, ultimately, the pillars of creation also, I was looking at the Trifid Nebula a little bit earlier, and those, the dark nebula that sort of splits that object up into the three, like the three-lobe plant, would also be considered Bok globules as far as I know, yeah.
Very cool. There's a lot going on up there.
There certainly is, yeah. So, as I said, for me, it was a great one to discover, and I look forward to continuing my search for better and brighter objects to image for you guys.
Yeah, well, let us know when you find new objects, and we'll look forward to seeing them with you next time.
Definitely, yeah. There's always something new to find down this side of the world, that's for sure.
Excellent. Well, Ben, thanks so much for being with us, and we'll see you in the next episode.
Fantastic. Looking forward to it. Thanks very much, Samuel. Thanks, everybody.
All right, take care. Welcome back, everybody. We're here with Dark Sky Conservationist John Barentine. John, thanks so much for joining us.
Hey, thanks for having me on the program, Samuel.
Yeah, it's our pleasure. So would like to start off the guest spot with the same question for everybody, which is, what's the one question that you wish everybody would ask you, but nobody does?
You know, that is an interesting question. It probably would be something along the lines of, well, you know, if you weren't doing what you were doing, what else would it be? And I say that because I had an odd journey through astronomy to get where I am now. And it would be, what, you know, what else, what might it have been? And there were times when I toyed with going to law school. I'm really into issues around public policy and law, having to, you know, do with interacting with science. Or my other passion is history and prehistory. And because I grew up here in the Southwest, I might have ended up as in archaeology or something similar to that. There's just so much of it around here. So just that, you know, what might have been, I guess, is the question. And I actually do have a couple of ideas of what might have been.
Very cool. So it sounds like it might have been a fairly circuitous route for you to get into dark sky conservation. How did that happen?
That's a funny thing. Around the time that I was finishing up graduate school and looking for a non-academic career, I went to work for the International Dark Sky Association, which is a non-governmental organization based here in Arizona that works around the world. And I got my job because of Twitter, as it turns out. And it happened to be that I was following the person who eventually hired me into that job. And they said, we have this position open to run something called the International Dark Sky Places program. And that's what I ended up doing for 5 years of the time that I spent there. And it was a complete gamble. It was kind of related to astronomy, but it was touching on these other areas about, you know, environmental science, and there was a little bit of policy work involved in that. And for me, it really checked a lot of the boxes. And I thought, wouldn't it be interesting to do that for a living? And it turned out to be quite the adventure.
Very cool. So what is preserving dark night skies all about? Like, why should anybody care about that? And what are some of the other factors that can be involved with keeping dark skies dark?
Well, the main thing that I can say to answer your question is to first sort of dispel a common misperception, which is that dark skies is just of interest to astronomy. And so unless that's something that really appeals to you, or you're a professional astronomer somehow working in that field, that it's not something that would really ever come up. And as it turns out, although in the early days of this movement, a lot of the people involved did come from the astronomy side, I would say that nowadays that's the exception. And that's a much smaller constituency than it used to be. And the reason is that we've come to understand so much more about the issue than we did in the beginning, when we thought, well, this is just a matter of whether astronomers are going to be able to see the night sky from their observatories. We now understand that the issues surrounding dark skies touch on everything from human health and well-being to the ecology and wildlife, public safety, energy security. Crime is one of the big things that now a lot of people are interested in, how outdoor light at night interacts with that. So there's really much more something for everybody in it now than there once was. And we're beginning to see how it's relating to these other social and environmental issues that are really high profile right now. And as a result, I think it's kind of an undervalued movement. And just as, you know, a few years ago, plastic pollution, for example, was something that was on everybody's mind. I think maybe this decade will be the one where a lot of people start to think about light pollution.
Well, I really hope you're right about that. It's definitely something that's near and dear to my heart for all the reasons that you just talked about, but specifically because I'm an amateur astronomer and I love to look up myself and enjoy the night sky, and it's my livelihood, just to be totally upfront about that. And so we just held an event here in Jackson called a Lights Out Challenge, where we were trying to get as many people as possible to turn off their lights at their houses and have businesses do the same, as well as the town of Jackson. So we could actually enjoy the peak at the Perseid meteor shower from downtown. And, you know, Jackson's a relatively small town. We have 10,000 people within the city limits, but there's still a lot of light pollution. And so we were hopeful that we could get enough people to turn their lights off and to have the town of Jackson do that as well. So we could actually see a difference in what the night sky looks like without those artificial lights at night. And we go to the next slide. I think I've got one of the images. So that's just one of the little meteors we got just above the Center for the Arts Center. You might be able to see it streaking across, but you can see that glow, that dome of light. So that's looking north towards downtown Jackson from a few blocks away from the Center of the Arts. If we can go to the next slide. So that's looking south. We caught another meteor kind of just going over the mountains. And you can see there's a lot less light pollution south of downtown Jackson compared to looking to the north. Let's go to the next one. So that's looking towards the northeast, caught a nice little meteor there in the bottom left-hand corner. You might not be able to see it in that small screen, but there's a nice one there. And I think the next couple images are the comparisons that we did from the different times. Yeah, so there you go. So the one on the left there is typically what we see from the Center for the Arts. So we do stargazing programs there a lot. It's like our choice location for public stargazing programs just because it's easy for people to get to, and it's a relatively dark location within the city of Jackson. We haven't done many for a while because of COVID, so this was our first one back. So usually what we see is on the left. During the event, the town turned off all the street lights alongside the Center for the Arts, and it was amazing to see the difference with about a dozen street lights off that don't have proper shielding, where there aren't shields that actually point the light down where you want it. And so we're going to take this image to the town and say, hey, look, if you just put shielding on these lights and directed the light downward, which is like the easiest fix to reduce light pollution, we could see so much more in the night sky. So we're hopeful for, with an image like this, we can make that argument and people will listen.
And, it's a really good point, Samuel, because that's another misconception that's fairly common among the public when we talk about dark skies, is that it necessarily means turning lights off. Now, I understand in this situation, it literally meant turning lights off as a demonstration of what's possible. But the idea in the long run, it's not really practical, right? We're not trying to send humanity back to the Stone Age or anything like that. We know that there are lots of good reasons that people have for using light at night. But we also have a lot of evidence that a good fraction of that light is ultimately wasted. And you mentioned putting the shields on the light, which just keeps the light directed down at the ground where it's needed and out of the night sky. And if you figure that a typical kind of light fixture that would be installed in the United States probably loses something on order of 20 or 30% of its light to somewhere that's not the intended target. And that may be over in the neighbors causing glare and nuisance, or maybe up into the night sky. And if we just reduced the waste, if we just kept the light where it was needed, then we would provide for all of those reasons that we have to use light at night, and we would keep it out of the places where it doesn't need to be. And remember too, that the night sky is just sort of symptomatic of what's going on in the overall environment, because half of the issue of dark skies is really talking about what's happening on the ground. And that's especially relevant for wildlife. And if you think about all of the species out there in the world that are under varying degrees of stress right now, whether it's from other kinds of pollution or whether it's climate change, that disrupting their behaviors at night is just piling on to those problems. So again, if we just kept the light where it was needed and we're not shining it into their habitat, or not shining it into the night sky, it's a win-win-win all the way around, right? Because not only is it good for the environment, it makes it easier to see the stars at night, it reduces the cost of providing lighting, which is something that's of interest to municipalities everywhere. It reduces energy consumption. And even if we move to a world where we're mostly using renewable sources for our electricity, we still need to be careful about how much total energy that we're using. And reducing waste is one way to bring that down. And so, if it's saving people money, it's making it better for, people and wildlife in the nighttime environment, and it's preserving the night sky. It's hard to imagine seeing somebody who says, you know what, I'm just not interested in those things. I really think there's something in this that appeals to everybody at some level.
Yeah, so I think about this a lot. Like, it's definitely like a win-win for everybody. And yet sometimes it's so hard just to convince people to turn their lights off. Do you have a sense of like why it seems to be an uphill battle sometimes, even though it's such a huge win-win?
There are several reasons for that, and some of them are, I think, universal, and a few of them are peculiar to the Western U.S. I think a lot of this has to do with the lack of awareness. There's those misconceptions or those preconceptions that people have. They hear the word dark, they think that that means unsafe. It's, not a place that they want to be at night. It's taking something away from them. Again, that sense that dark skies means we have to put up with, less light where we need it, which is not the case. And some of that is fueled by a distinct human psychology that makes us afraid of darkness. We all kind of think of in a stereotypical sense about children being afraid of the dark, but believe me, adults are also very afraid of the dark, and we shouldn't play that down. And I think especially, it's an important issue for women who in many cases, they don't feel safe. The feeling of being safe is important. And we want the lighting that we use to provide actual safety, because in a sense, it would be worse to convey a false sense of security about something that's not really backed up by the facts on the ground. So in my world, what I want to see is, I want to see the lighting that we used quite well, that conveys a real sense of safety and security, because it really is making the situation safer for people, and especially for women who are traveling alone at night. That's a serious concern, and we should never play that down. The thing that's peculiar a bit to the West, we just encounter it more out here, to be honest, is difficulty in conveying these ideas around private property rights. And a lot of people are averse to the idea of any sort of policies or rules that restrict the use of their light, because it's back to the sense of, it's my property, I should be able to use it however I want. And there's even a way that I think we can fit these ideas into that worldview that respects property rights. I think Dark Skies does. And it does so because it has a sense that with rights come responsibilities. And if I talk to people about this issue who are very property rights oriented, and I tell them, your neighbors have property rights, your neighbors should be able to enjoy their property as well. And do you want to be the neighbor of the person who has the bright security light on all night across the street that's shining onto your property? And they think about it a little and they realize, oh, right, this is a two-way street. And I have seen the opinions of people for whom this is very important. And again, I don't downplay what they think and feel, because it's important. But when you kind of frame the argument a little bit differently and give a little bit more information and say, look, we're not coming in to take things away from you and to impose on you. We're trying to find the solution that respects your rights and the rights of other people. And they get it. And you see that kind of dawning on their face, like, oh, okay, I know what you mean. So I don't think those things are mutually exclusive, any of them, that we can have dark skies, we can have safe and secure cities and streets and sidewalks and parking lots, and we can have respect for property rights. And all of these things are compatible with one another. And the secret to making it all work is we just have to think differently about how we use outdoor light at night.
Well said, John. It's like you've done this before.
I've been around the block. What can I say?
Yeah, I mean, you actually helped me out years ago when I was first trying to rewrite the outdoor lighting ordinance here in Jackson. So thanks so much with that. We did get some amendments passed with that, and we still have another round that we're working on, but we'll get there.
There's always work to do.
Yeah.
I had a quick question on the, I guess, the technology side of it. As we've advanced with different types of lighting solution, is there preferred wavelength that is best? Yellow lights versus blue lights, that sort of thing. And the advent of LEDs being more efficient, but probably also narrower wavelength bands that they emit in. What's the kind of recommendation there?
That is a fantastic question, and it is something that's become really a top shelf issue for us in recent years. And you mentioned LED, and it's really being driven by that. The adoption of LED has changed the color of the night. And we even have some dramatic photos of cities that have converted over their street lighting from the old technologies like sodium vapor that was this really kind of golden, warm color to this sometimes described as harsh white associated with LED lighting. And it's not just that perception. And a lot of people don't like it. I've heard it described as prison lighting or hospital lighting. And why would you want that in an outdoor space? And beyond the aesthetics, it's a really good point. All of that more blue colored light entering the nighttime environment is really almost completely new in history. There are very few previous technologies of lighting that involve so much blue light. And it's really problematic for biology, as it turns out. A lot of organisms they have a circadian rhythm that's set by the rising and setting of the sun that governs all kinds of activities in the body. And we're part of that biology, so it affects our sleep, our hormonal rhythms, our overall sense of well-being. But that blue light is also much more likely to scatter as it moves through the atmosphere, right? It's the reason that the sky is blue during the day and not some other color, because it just turns out as a quirk of nature that's a color of light that really strongly interacts with the small particles in the atmosphere. And we've demonstrated now with data that it actually does change the brightness of the night sky over cities. And in a bad way. And so there's good reasons now to deal with this problem, which in the early days of LED was really dictated by limits of the technology. But now we don't have to rely on that really strong bluish emission of light in order to get the energy efficiency that was so important to the different levels of government where they've adopted this, right? Lower cost, lower carbon emission, et cetera. And now even kinds of LED that are distinctly warm in color, like amber LED, is now becoming competitive on the outdoor lighting market. And parts of the world where they're really concerned about these impacts, they now have the option to choose these other kind of warmer colors of light. So that color question, that's at the heart of what we've been working on in, I would say, the last 5 to 10 years. And finally, the technology is catching up to the point where we can put really high quality LED lighting out there that doesn't have to be an environmental disaster from the get-go.
Very cool. Thank you.
Any other questions for John from the other co-stars?
Yeah, I had a question about the sources of this light in the dark skies, because I know there's like a push for me personally. I could turn my lights out and cities could also remove their lights. But what about businesses and things like that? Like, what's the distribution of where the light is coming from and where can we have the biggest impact?
That's another good question, Lauren. And it's one where we have a guess that's not super well informed by data. And the reason for that is, if we look down from satellites or from the space station on the Earth at night, we can get really good images of cities at night. But connecting up the kinds of land use, so whether it's, is this, if you have a map and okay, well, this is a residential part of a city and it contributes a certain amount of light, and we think this land over here is business or government or some other kind of use, you can start kind of parsing it out a bit. And it turns out that it really depends on where you're at in the world, and certain regions of the world tend to contribute more or less in those different areas. So, Europe, North America, parts of Asia, commercial lighting is apparently a pretty big contributor relative to something like residential. You go to less developed parts of the world, it tends to be more residential and other uses. Agricultural use of light at night is a surprisingly big deal in certain parts of the world. And so then that suggests the kind of strategies that you would pursue depending upon where you were trying to achieve results. And you also want to try to frame it, I think, in, make it a win-win for people. We can go in and write laws that tell business owners, you can't do this and this and this with your lighting. And in my experience, government doesn't like to be the enforcer. Everybody likes to write the laws because it feels good, but when it comes down to implementing and enforcing them, no one wants to do it. So it's easier to write laws that are easy to comply with and incentivize certain kinds of behaviors. And we've had some success with businesses in that. And it does come back to this sense of awareness. If you make them aware of the issue, how they're contributing to it, tie it to their business model or what they're trying to achieve as a business or a business owner. Sometimes that's presenting a good image to a community that works well in smaller places where business owners are much more identifiable in the community. In bigger cities, it's more about lowering costs and having an attractive storefront when people drive by, that kind of thing. And those different approaches can have success depending upon the details. But as time goes by, we hope we're going to get increasingly granular information about where the lighting is distributed. Because if we fine tune these mitigation approaches to whoever we're addressing, whoever the landowner is or what they're using it for, we think we can get better outcomes that way. And we don't have to kind of come in with the threat of writing new laws that govern business that in a lot of cases just aren't popular and have to rely on that. So that's a great question, is how do we figure that out? How do we better target those strategies to the way people are actually using light out there in the world?
Very cool. Thanks.
So I have a question. I live in Chicago, and it's kind of difficult to conceive of Chicago not having an insane amount of light pollution. And I'm curious, I guess, how, like, is there a certain density of people which you kind of just, there's no real point, or I'm sure there's a point in always trying to reduce the light. But like, I guess urban versus rural, like, is there more bang for your buck and like keeping a dark area dark than maybe just kind of giving up on the cities a little bit?
No, that's a good point. And it's something that it's sort of an ongoing debate in the conservation / technical side of this business. We have so many resources and X number of people that are willing to work on this problem. And we only have a certain amount of political influence, so we can only change laws to a certain extent. So where do we best target our efforts is the question. And as far as anybody can tell, it's a little bit of both. And we've been trying to sort of lock down these places that are still dark and to keep them that way as much as possible. The problem is that the reach of light from cities is bigger than we once thought it was. And to give you an example from out here in the West, I have several times stood at the south rim of the Grand Canyon here in Arizona at night and looked west and seen the lights of Las Vegas on the horizon, which is, the crow flies, is about 175 miles away. And it's not a lot of light, but it's there. It's a presence. And if you are an environment, a very sensitive species or something like that, if you're a migratory bird and you need darkness and you're navigating by the stars, you might get drawn off your course because of that light. So if you work that out, that means that the sort of, on a flat Earth, the footprint of Vegas in terms of its light is at least 100,000 square miles, which is enormous, right? And we don't have many big cities out here, but if you start to think, well, there's Las Vegas and there's Salt Lake City and Denver and Phoenix and all of these different cities, these footprints are gradually growing together. So at some point, even if we want to protect the places that are still dark, we've got to work on the cities. And we think that the next frontier really is the built environment and convincing people who live in cities that the choices that they make about lighting in their cities have this impact very far away, and it's disproportionate. And that's really hard, admittedly, to try to convince somebody who lives in Chicago, why should I care about what the conditions are like in rural northern Minnesota? Your light reaches that far. And people don't think about that. I will give a brief plug to the folks at Adler Planetarium in Chicago. They've been working on light pollution for years, and they're really moving some stuff in Chicago that's worth taking note of. And if anybody is going to convince Chicagoans to change their light, it's probably going to be the Adler folks. I mean, they just have so much sort of cachet there. But yeah, that's something that we're still trying to work out, is, relatively speaking, how much effort should we be putting in the cities versus the dark areas? We have a lot of them in the United States, at least in the lower 48, are locked down now. They're under some form of protection. So I think in the long run, we've really got to change some hearts and minds in the cities if we want to keep them that way. That's a good point, Nora. Thank you.
Yeah, that's really interesting. Thank you.
Well, John, oh, sorry. Danny, go for it.
Oh, it's okay. I think we're way over time. So
Yeah, we definitely are. Per
It's
usual.
okay. Thank you, John. It was wonderful.
If you got a quickie, go for it.
I was just going to say, so I'm a physician. So I'm kind of coming at this whole concept from a very different angle than most of the other folks on this call, or on this this production. But as I'm sure everybody on this group is aware, different wavelengths of light impact the body in very, very distinctly different ways. And it always amazes me how many folks struggle to fall asleep at night, and it turns out that they've been exposed to just like hours of blue light, immediately before trying to fall asleep, and then wondering why this is a problem. And so I would love for there to be some sort of like health related rationale woven into the bigger picture here, because maybe there would be more buy-in. And I think it's a hard sell sometimes for folks, to understand how this thing that's pretty amorphous, or at least is a pretty amorphous concept, can really dramatically impact their own health and well-being. But anyway, just my 2 cents. So thank you.
Oh, sure. And just to briefly follow up on that, Danny, about 5 years ago, the American Medical Association issued a report that identified blue light, and even from outdoor sources like streetlights, as a potential health hazard. And of course, you talk about harm to human health, and that gets the attention of a lot of people. The main disconnect to this point has been, where do we get most of our light exposure? And you're right, by and large, it's people staring at screens too late into the night. But I think about cases where people live in places where they have a street light just outside their window. And of course, in bigger cities, this is almost impossible to avoid. And we even have some suggestions from data from the world of sociology, marrying up with this light pollution research, that people in poorer neighborhoods, people of color, are disproportionately impacted by this. And so all this extra light exposure that some of them are getting is an issue of social equity that I hope eventually that we will confront. Because if we talk about this as being a public health issue, and we want to try to do something for the health of everyone, we do need to address those disparities that are based on where people live or what their income levels are. And light at night, even from outdoor sources, is very definitely part of that.
Thank you.
Well, as you can see, it's time to start getting ready for stargazing programs here in Wyoming. And we've already gone way over time, as we usually do, because we're all just so passionate about what we do here, which is a really good problem to have. So John, thank you so much for joining us this evening. Really, really appreciate it, especially on a late notice. Thanks to all the co-stars for being here as usual, to our streaming master, Gavin, and to all the folks who make the Cosmos Show possible from behind the scenes, especially all of you who are watching the Cosmos Show. Thanks so much for tuning in, and we'll see you again in a couple of weeks. Until then, be well, and don't forget to look up. We'll see you next time. Bye.